Today we're going to be looking at modeling electrical systems. I'm going to start off by giving you an overview of each type of electrical element that we will deal with, and we'll be focusing on how we would deal with these things in terms of electrical systems. If we make an analogy to how we went through mechanical systems, in electrical systems we'll be learning how to deal with resistors, capacitors, and inductors, whereas in mechanical systems we were learning how to deal with masses, springs, and dampers. Next, we'll take a look at the relevant electrical laws that we can apply to our system to derive their equations. The laws that are relevant here are mostly Kirchhoff's laws, the current law, and the voltage law. The analogy here to mechanical systems is that in mechanical systems we learned how to sum the forces and how to sum the torques or moments. In electrical systems we'll be summing the currents and the voltages. Finally, I'll show you a couple of complete examples of circuits. We'll model the circuit and then we'll see what the equation means in terms of the things that we know about systems. The system order, linearity, time invariance, and so forth. So let's start with an overview of electrical elements. We have three electrical elements that we will look at. We'll look at a resistor, which has resistance R, a capacitor, which has capacitance C, and an inductor with inductance L. Let's look at what equations we know for each of these individual elements. First, with the resistor, we have an equation for the voltage lost across the resistor. And this equation, as you may know, is V is equal to the current times the resistance. Now, when we're looking at this element in terms of systems modeling rather than in terms of simple circuit analysis, we have to pay attention to which things are signals and which things are system parameters. In this equation, R is a constant. It's a system parameter. The things that change over time are the current and the voltage. The reason that we have to pay attention to these things changing over time, now that we're looking at electrical elements in terms of systems, is because when we analyze circuits as systems, we're not only paying attention to the steady state of the circuit, we're also paying to the transient behavior of the system. In other words, in the past you've probably analyzed circuits as though the voltage and the current in these elements did not change. However, when you apply an input to a circuit, and that input is a signal that changes over time, certain quantities like the voltage and the current will change over time. And in systems analysis, we are concerned with how these output signals like voltage and current change over time. Next, let's look at the capacitor. We also have an equation for voltage lost across the capacitor, and that equation looks like this. The voltage, which is also changing with time here, is equal to the charge in the capacitor, which is changing over time, divided by C, the capacitance. Here, the capacitance C is the system parameter that does not change with time. Q, the charge, and V, the voltage, do change with time. With the capacitor, we want to recognize that current is defined as the derivative of charge over time. Now, let's see what happens when I take the derivative of this equation. If I take the derivative with time of both sides of this equation, Now I can plug in the value of dq dt from the previous equation, and I get this relationship. This relationship is going to be useful for us to note, since we're often interested in how voltages and currents change in the circuit. The reason why we're generally interested in how voltages and currents change is because the two Kirchhoff's laws deal with voltages and currents. So what I'm going to do is I'm going to erase this derivation, and I'm going to put this other equation up here as one of the two equations that we want to note as being relevant to capacitors. Finally, let's take a look at inductors. We can also write an equation for the voltage across an inductor. That equation looks like this. Now that we have our equations relating the changing signals in each of these elements, voltage and current, we can use this information to derive the equations for some circuits. But before we go ahead and see some circuit examples, I want to review the two laws that we're going to apply: Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is about what happens to current at a node. A node is a place where more than two wires meet at a junction. So, for example, we might have a node like this, where the current comes in here and leaves the node like this. Kirchhoff's current law says that the current leaving the node is equal to the current entering the node. So if the current here is I1, and again I'll say that this is a function of time, and here we have a current 2 that is a function of time, and here we have current 3 as a function of time, Kirchhoff's current law says that I2 of t plus I3 of t, that is the total current leaving the node, is equal to I1 of t, the total current entering the node. This law applies no matter how many wires you have coming in or leaving a node. If you have 2 wires coming in and 3 wires leaving, you would have 2 currents on one side and 3 currents on the other side. You always state that the sum of the currents entering the node is equal to the sum of the currents leaving the node. The other law we're going to apply when modeling circuits is Kirchhoff's voltage law. The voltage law states that at any given instant of time, the sum of the voltages around a loop is 0. For example, suppose that we have a battery and we have a number of elements in this circuit. Let's suppose that the voltage provided by this battery is called the voltage applied, and remember that this changes with time. The voltage lost in each of these elements will change over time, as we saw when we were analyzing the elements. Let's call this the voltage lost in the resistor at time t. And let's call this the voltage lost in the capacitor across these 2 points at time t. And here we'll call this the voltage lost in the inductor at time t. Kirchhoff's voltage law tells us that at any time t, the voltage applied is going to be equal to the voltage across the resistor at that time plus the voltage across the capacitor at that time plus the voltage across the inductor at that time. It's important to note that this law also is true not only in the steady state, that is, after all of the signals have stopped changing, but also in the transient response, that is, the time during which the voltages and currents are changing. Now, let's take a look at a couple of examples of how to model circuits, and let's look at the equations that we get and see what we can determine about the system from the equations. For our first example, let's suppose that we have a battery, and that this battery has a voltage of V applied at time t. In this circuit, I'm going to also put a switch. In a moment, I'll talk about what the switch means in terms of our system's modeling. In this circuit, we'll have an inductor, a resistor, and for now that's all. Just like we did when modeling our mechanical systems, one of the first things we need to do here is identify our input signal and our output signal. Here, our input signal is going to be VA of t. This is the input. This explains why I put a switch in this circuit. We need to be able to say what the voltage applied is at some given time. By putting in a switch, I've allowed us to be able to leave that switch open at times less than 0, and it'll allow us to say that we're going to close the switch when time is equal to 0. What kind of an input would this give us if we close the switch at time equals 0? A step input. You can see this if we imagine what the voltage applied would be over time. When time is less than 0, the switch is open, so the circuit, not being closed, has no voltage being applied, 0. At time t, the switch closes. Since the battery is a single voltage source, the voltage would suddenly jump at time t up to the value of the battery. And since the switch remains closed, the input, the voltage, will remain at that level. Putting a switch into a circuit allows us to apply a step input to the circuit. For the output in this case, I'm going to say that the output is the current in the circuit over time. I won't say that the current is the current through any one of these elements. Since we only have one loop, the current in each element will be the same. Now, let's see if we can derive some equations that will relate the applied voltage over time to the current in the loop over time. To do this, I'm going to label the inductance of this inductor as L, and I'm going to label the resistance of the resistor as R. Next, I'm going to apply Kirchhoff's voltage law. Kirchhoff's voltage law says that the voltage that I am applying from this battery will be equal to the sum of the voltages lost in each of the elements. So we can write this kind of an equation. Since I've already applied the current law in my assumption, we're done here. We have an equation that relates the input signal, the V applied, to the output signal, the current in the loop. What can we tell about this system from this equation? The first thing we can tell is that this system is a first-order system. The way we can tell that is that the output shows up as the first derivative and the zero derivative, but no higher derivatives. We can also tell that this system is linear because there are no squares of any of the variables. There are no multiplications between variables, such as di dt times I, and there are also no sines or cosines of the variables or their derivatives. We can also tell that this system is time invariant. We can tell that because time only appears in the functions and it does not appear as a variable on its own. Now, since the system is first order, can we predict the shape of the output? If we know that we're giving a step input, we can predict what the output will look like. We know that the output will look like this. Let's draw time, and the output, which is I of t, the output will look something like this, a first order step response. Remember that a first order step response is characterized by its time constant. Can we figure out what the time constant is just from the equation? Let's see if we can. Remember that the time constant is related to the slope at 0. If we take the slope at 0 and we draw that line up until it intersects the steady state value, the time that it intersects is the time constant. Could we get this just from the equation? First, let's see if we can get the steady state value from this equation. We can see from the plot that the steady state value is what happens when di dt, that is the change in current over time, has become 0 or very close to 0. Let's try plugging that into our equation. Now, let's solve for current. This whole term goes to 0. So, we have the current is equal to V applied over resistance. Let's go label this value in our plot. Here's the steady state value, which I've dashed here. Let's label this as V applied over resistance. Next, could we find the slope of the response at time equals 0? Let's see if we can. What we're going to do is we're going to plug in t equals 0 into this equation. When we substitute t equals 0, the current is going to be 0. That's because the current has not yet had any time to respond. We can see that right here in our plot. When time is equal to 0, the current is 0. Let's plug that into our equation. Now, let's solve for di dt. Remember that di dt, oops, I should have 0 here. We want to find di dt at time 0. That will tell us the slope at time 0. So now we know the slope at time 0, and we know the steady state value. Can we find the value of the time constant t? Sure we can. Let's do it like this. Let's look at this, write the slope from this plot. The slope of this line from the plot is equal to the rise over the run. The rise is VA over R, and the run is capital T, the time constant. So the rise, VA over R, divided by the run, the time constant, that's the slope of the line, and this is also the slope of that line. I'm just going to write VA instead of VA at 0, since in a step input, the value of the input is the same from 0 on to infinity. Now, let's solve this equation for the time constant. I'll multiply both sides by the time constant and then divide both sides by VA over L. Now, let's simplify a little bit. The time constant of this system is equal to the inductance L divided by the resistance R. We can design this circuit to be faster in its response or slower in its response by changing the values of these two components. If we make the inductance be larger while holding the resistance constant, the system will respond slower because the time constant will be higher. On the other hand, if we would reduce the inductance, the system would respond faster. Also, with the resistance, as we decrease the resistance of the resistor, the system responds more slowly. As we increase the resistance, the system responds more quickly. This kind of an analysis can be really useful when we're designing circuits for some application. If we know how fast we need the system to respond, we can select appropriate components to give us that speed of response. Let's look at one more example. This circuit is going to be similar in that we have a battery providing an applied voltage over time. We also have a switch so that we can apply a step input. This time we're going to have not only a resistor and an inductor, we're going to also add a capacitor. Similar to the last example, we need to start by identifying the input and the output. The applied voltage is going to be the input, and the output, once again, is going to be the current in this loop over time. We're going to apply Kirchhoff's voltage and current laws first by applying the current law to recognize that the current will be the same in each of these elements. And secondly, we'll apply the voltage law to say that the applied voltage at any time is equal to the sums of the voltages in each of these elements. I'll label these elements with their parameters: resistance, inductance, and capacitance. Now, I'm going to write the equation that VA at any time t is equal to the voltage lost across the resistor plus the voltage lost across the inductor plus the voltage across the capacitor. Next, I want to get rid of this Q on the right-hand side of the equation because Q is a signal, not a system parameter. It's changing over time, but it is neither the input nor the output. However, I know that the derivative of Q, that is charge in the capacitor, over time is equal to current. So what I'm going to do to get rid of Q is take the derivative of both sides of the equation. I'm going to recognize that this term is equal to I of t, since current is the change in charge. And I'm also going to rewrite this using a dot to represent derivative with time and a double dot to represent the second derivative, just so this will be easier to write. So what can we tell about this system from this equation? First of all, we can tell that this is a second order system because we have the second derivative of current in the equation. We can also tell that this is linear because there are no sines and cosines of any of the variables or their derivatives, and we also have no squares of the signals or signals multiplied by each other. We can also tell that this is time invariant because time appears only as a function and it does not appear as a variable on its own. So if we assume that the input is a step input, can we predict what the response will look like? It will look like a second order step response. We can draw time on the x-axis and current on the y-axis, and it will look like one of three possibilities. It might look like this, or maybe it will be critically damped. The red one is underdamped. It may be critically damped, as fast of a response as possible with no oscillations. Or maybe the response will be overdamped, slower than critically damped. Can we tell from the equation whether it's going to be underdamped, overdamped, or critically damped? Or better yet, can we figure out the properties of the second order system, the natural frequency and the damping ratio, just from the equation? Let's see if we can. The most straightforward way to do this is to compare our equation with what's known as the general equation of a second order system. You first saw the general equation of a second order system in the first problem set. The general form looks like this. This is the output. Double dot is equal to some gain, G, times the natural frequency squared times the input of T minus 2 zeta omega n y, that is the output, dot minus omega n squared y of t. Let's rearrange our equation to try and get it to look like this standard equation. The first thing I'm going to do is I'm going to get I double dot of t alone on the left-hand side of the equation. That's because in our general equation, y is the output. In our equation, I is the output. So in order to compare these two equations, I'm going to get I double dot by itself on the left-hand side of the equation. Now, I'm going to make an analogy between these two equations. This tells me that 2 zeta omega n is going to be equal to r over L, and omega n squared is going to be equal to 1 over LC. I'm going to write that out here. First, I'll use this equation on the left to solve for omega n. We find that the natural frequency of our system is equal to 1 over the square root of LC. Now, I can use this to plug it into the other equation in order to find zeta. Now I'm going to solve for the value of zeta. I could simplify this a bit by taking this L into the square root as L squared. Then canceling out one L in the numerator with one L in the denominator. And that tells me that my zeta is equal to R over 2 times the square root of C over L. So is this system underdamped, critically damped, or overdamped? You get to choose what it's going to be based upon the values of the components that you use in the circuit. Remember that a system is underdamped when zeta is less than 1, that it's overdamped when zeta is greater than 1, and that it's critically damped when zeta is equal to 1. You can choose the values of your components to set the value of zeta to determine how the system would respond when the switch is closed. Similarly, you can also set the natural frequency of the system by setting the values of L and C. Setting the natural frequency of the system will be important if you ever expect your system to receive a sinusoidal input. In that case, you would want to make sure and set L and C so that the forced frequency of the system doesn't ever overlap with the natural frequency. Especially if zeta is much less than 1, you would cause some problems in the system as the system begins to resonate. You can use this approach of comparing the standard equation to your equation for any second-order system to find equations for the natural frequency and the damping ratio zeta. This is another approach that's very useful to us when we're designing a system, so that we can set the properties of the system, such as the damping ratio and the natural frequency, to be appropriate for what we want the system to do. Remember that once we know the natural frequency and the damping ratio zeta, all of the other properties of the step response are defined, including the peak time, the rise time, the amount of overshoot, the settling time. All of those things are defined in terms of these two parameters. So once you've found the equations for these two parameters, you can also find equations in terms of the system parameters, such as the capacitance, the inductance, or in the case of a mechanical system, you can do this in terms of mass, the spring constant, the damping ratio, and you can solve for the values of your system parameters in terms of what you want the overshoot to be, or how fast you want the system to respond, what you want the rise time to be, or how long you want it to take for the system to settle. You can also set the values of these parameters in order to prevent disasters such as a forced frequency overlapping with the natural frequency.